Okay, welcome everybody. This is the Tegra K1 Tools Lab. Sorry, GDC 2014. Okay, I'd like to put a big thanks out to Crow Team. They've donated Serious Sam 3 for us to work with today. So you'll be working within their code actually and be able to play segments of the game. And this is not a final product, so please be aware. And we have also planted bugs and performance pitfalls into the game, so you won't be able to, it's not going to be representative of what the final game perf is going to be to begin with. And on that same note, we're also going to start in debug mode. So performance will be lower as you would expect while you're working in a debug compiled game. But later on, we're going to switch to release builds, and you'll see the performance pick up over time as we go through the lessons. Okay, today's hardware. Next to you is a Tegra K1. This is the 32-bit version. You may have seen our announcement that there's also a 64-bit version coming. This is a quad-core, or 4+1 technically, and it's a Cortex A15 and the R3 variant. And this is not an announcement or a preview or a leak, so please don't start any rumors. Really what this is it's an internal dev kit that we use to help make it easier for these type of shows and even for our internal developers, because it's easier to carry around and to work with games like Serious Sam 3 that actually require a controller, right? It's going to be a single piece. And it's a little more friendly and rugged to work with in these labs. Okay, so our agenda for today will be starting with Nsight Tegra. This is to do all the CPU side development of your game and debugging of the game. How you would typically start any new project. And we'll move on to the Tegra System Profiler, which is going to focus on optimizing for the CPU. And then finally, the Tegra Graphics Debugger, which is going to be optimizing and debugging the GPU side of things. So you'll be able to do all sorts of great timing and experiments there. All right, Nsight Tegra. So many of you are coming from the PC and console world, where you're probably already using Visual Studios. It tends to be the most popular. And it's just such a great experience. Most people find that it becomes very hard to leave that platform and go ahead and start working with different tools. So what about Android games, right? What has your experience been? Well, we're finding many of the people that we talk to are having quite a hard transition, and they don't necessarily like working in Eclipse. They can't really wrap their mind around all these MIG files and everything within it, and debatably, there's different levels if you're going straight to GCC versus using the NDK MIG files. So different levels of complexity there. And when you need to get down to optimizing and getting the right compiler flags, you have to jump into those GCC docs, and there's multiple versions all over online, and they're a little cryptic, and you never quite know what you're getting unless you're an expert and well versed in that, or have a good Linux friend on hand. Or maybe you've tried GDB to do the debugging. I've heard a few people tell me they've wanted to cry having to type those things into the console, and just even the effort of setting up a debugging session can be a little intense. So with Nsight Tegra, you can author, build, deploy, debug your game, debug it visually more specifically, just the way that you would expect it from your previous history as a PC or console developer, and you're doing it right in your favorite tool that you've always worked with. And we're supporting Microsoft Visual Studios 2010 through 2013, and 2013 support was just released yesterday. So you can go ahead and download that through the NVIDIA Dev Zone and through the Tegra Android Developer Pack. All right, Serious Sam 3. So I'm going to switch here to the setup. We'll go to our PC, look at the Project Explorer, and go to the Serious Sam 3 launcher. It's quite a bit ways down towards the bottom. Right-click on that and go to the properties. Now for any new project, we have a few different options, right? You can go completely native and get just what you would expect here, like any Visual Studio's project where you can set up your C++ and your Java and your linker options. In this case, the Crow team did things a little bit different. They have used a new feature that also was just released this week, which is our external build system. Their game is cross-platform. You know, it's been around for a long time. Hopefully you've already bought it on the PC and consoles, and hopefully you know, in the future on Android. And so they've established themselves with using Jam to do their compiling. And so if you look at the nmake page down here towards the bottom, you can see the commands that they're using to launch their build. So if you're doing something similar, right, you would simply hook up your build command and your clean command. We support other systems too, right? We actually have a simple system for importing for importing NDK projects. And we also have the full native experience, but in this case, I just want to walk you through this new one so that everyone can see. So they have their build and compile commands and additional search paths that's going to assist for IntelliSense to get all of the proper syntax highlighting, let you know if you have any errors. So those are the main paths that you're going to worry about setting up, or not paths, but full commands technically. And then debugging is going to be the next most important thing. So after you've built, we're going to want to debug this, and in order to debug, because you're not using the native MS Build experience for Serious Sam 3 specifically, you'll want to supply the override APK path, and this is going to tell us where the output has gone, along with the symbols information. The symbols, this is interesting, I'll speak to it for a minute, because it's different from what you might experience on the PC. Right, on the PC, you're used to getting PCB files and DLLs or executables, and they've separated out that debugging information. PDB. My tongue is already tied. Yeah, so you're used to having that information separated out. Well, in Android and Linux, it's actually going to be combined together. When you compile it, the SO file, which is the equivalent of DLL, will have both of them in there. And then in a future step, typically, you would strip that out after the fact with an additional command line. And this means in the Android process, you need to be aware that there's actually going to be two copies of your executables. One that has come out through the standard compiling directory, and then a second one that's going to be used for packaging. And how the Android system works is that they're going to package up the stripped version, send it down to the device, and the debuggers are going to look at the other one on the PC that still has the symbols in there and correlate those two back together. So the best way to figure out which one is if we go back down to that directory that I had you guys open earlier, then we have a batch file that I've provided here where you don't have to open it up for edit. I'm just showing the internals from here that we're using Cygwin and using the nm command to dump the contents of that to the screen. And I'm going to run that for you so you could just see what that's going to look like. Everything's going to show up here. You're going to see a lot of actual file paths listed here, and that's how the system's going to correlate everything back together. Okay, now we can go back to the lesson that we were about to start and just hit F5. And here you can say no. It's not a requirement. This is just because the way that to build this time, because the way that the Microsoft Makefile style build system works is that it relies on the tool that you're calling, in this case Jam, to do the smarts about whether or not the files have already been compiled so that it doesn't redo any of the work. And during this process, well, that went very fast, so I'll have to speak to it even though it flashed by your screen. We're doing all the work for you. We're pushing that executable down to the device. We're going to launch it in the special mode required for debugging. We're going to do all the port forwarding for you to attach and launch the GDB servers and the Java servers to connect everything together and route all the information back to the PC for you. And within another second or so, hopefully you already have Serious Sam 3 started and running on your device. So why don't I switch up here. Okay. We're going to hit the A key once to enter, and then we're going to go into single player, campaign, and we'll hit the up key one time. And here is custom levels. We'll go into custom levels and then up twice to the no enemies villa scene. So this is our little sandbox to start working in, because a lot of game developers are going to just be launching a much more simple level rather than going into a complete game when they're iterating right at a rapid pace. Well, the first thing to notice here in this level, I mean, you can use it, it's playable. Performance isn't necessarily fantastic. You'd expect a little more just because there's no enemies in this level. But that's partly because there's debug and other perf pitfalls that we've put in for future parts of the lesson. And what you'll notice first is that these trees seem to be casting shadows, and yet it seems to be night out. That's a little weird. And if we look up, oh, there's the sun. Clearly something's wrong with our skybox here, right? So let's go figure out how to fix the skybox. I'm going to switch back to Visual Studios, and if you go to that text file I mentioned earlier, the copy paste, this is the name of the function that you're going to want to find. So you can use Control-C, Control-F, and Control-V. So Control-C from here once, select into the cube renderable CPP file, Control-F and Control-V, and that will bring you into the function where we want to start. And from right here, we are going to go to line 236, and we're going to put a breakpoint. So the breakpoint is there. We just hit it. This is happening every frame. It's going to go ahead and render that cube map, right? And then why don't we just continue debug and see if we can figure out where this thing is going. Well, this one's probably pretty obvious, but we're going to hit F10. And sure enough, we're walking right into that can't render anything section, and it's going to early out and exit. So if you were to continue, obviously it would remain black, but instead we're going to do something a little different. We're going to go to the yellow cursor, and we're going to drag that down to line 241, so just the next available statement, and drop it right there. And it's just that easy to change where you are in the code. And we'll hit F5. And what it's going to do is it's going to just let the program continue. And it's going to come right back and hit that same breakpoint again in the rendering. But now what you're going to see is if we switch back to the shield, all of a sudden the skybox came right there. So that's pretty cool. I mean, that you could go through and you didn't have to printf, you didn't have to recompile or restart and deal with the restarting the app and all that, just to make some minor little memory change, moving the instruction pointer around, right, to get back there. So that's a huge time saver on its own. And now we're going to see if we can get this to work permanently, right? So if I come here, we get tooltip highlighting. So if you just hover over the cube variable, you're going to see that it is 240, which is clearly not 0, so it can't be that one. Oh, it's that one. Enabled is false. We can come over to the call stack. Hopefully you have that open already, and if not, you can get to it through debug window, and it should be right there. But yeah, it should be already open in this panel on the side. And what you'll notice is that enabled is actually passed in as an argument, We'll walk up one level, and we'll see the correlation here that some horrible programmer left it in as false. Who could dare do that? Oh, sorry, it was actually me, my plant, just for the session. Okay. So what we could do here, which is also great, is that we can come down to the bottom, go to the locals window, see all the locals that are here even though we're not even at the top of the call stack, and we can double click on that enabled variable, just type in true there, hit enter, and the value's changed. It turns out in this case it's static. You could do the same thing with an argument, but it's going to pass through. And we'll hit F5 to continue. And remove that breakpoint, continue again. And you'll see that, that now your game on the device is actually just going to continue rendering that sky map, no problem, right? So we've fixed a memory error, and we can just continue without even restarting the app. But now we're actually going to fix it for real. We'll stop the debugger. Now that we're all back at Visual Studio, I've stopped the debugger with the red key, and we're going to come up to enable, and we'll just type true in there. And then while we could hit the build key, why don't we hit the build key this time? So you don't even need to save it. Visual Studios takes care of that for you through the dependencies. Hit the build. It's this one right here. You'll see that it's going to recompile a few of the relevant files, and SiriusSam actually does something pretty cool. They have a built-in Lua system for issuing commands, and it actually parses the headers for certain macros. I could show you those here, such as this meta and the version, and here's the ones that we've planted, and it will parse those out and prepare those for their terminal system. So within a second, you'll have it finishing up compiling as it finishes building the .a files, which are equivalent to libs, and then making a .so, which is equivalent to the DLL, and finally packaging it up into the system, APK, which needs to go onto the device. Take a look at our source code, and we're going to go to this file that I prepared for you before, just so that people don't have to worry about minor spelling mistakes, things like that. We're going to grab that first one, the NVIDIA lesson assert. And actually, I believe for you guys, if it doesn't already look like, oops, I'm on the wrong line. If it doesn't already look so, you're like this, you're going to want to add a =1 on the end. We're going to copy that, we're going to paste it in here, and hit enter. So what's happened is we've triggered an assert by modifying by forcing through the script it to go down a code path that has the assert in it. And in this case, you get a trace breakpoint trap. And this is actually not a real assert. If you were, I'll explain this in a second, but hit the break, scroll up, and I have a little explanation for you. If you were to actually use the standard assert statement, the source code does something very similar, but it doesn't raise a sig trap. It raises something else, and that is going to be a fatal, non-recoverable signal. So we highly suggest it, and SiriusSam had already done a similar thing where they have their own assert being defined that raises sig trap. And this is a great way. It's equivalent to the debug break function on Windows or ASM int3 if you're doing the assembly. And that's how we're getting back even on breakpoints here without having to worry about recoverability issues. So you can see if you touch your device that that it's completely paused, and that's because the debugger has hit effectively a code-based breakpoint rather than one that's implemented in the debugger. And if we just hit continue, then everything continues as you would expect it to. Great. So I'm going to skip this small section, but you can do the same exact thing. You'll have the same exact experience with exceptions, but depending on the type of exception and how you're coding to it, you may not be able to recover from it, just like a standard PC application. And you'll get that same basic pop-up, and it'll tell you what the signal type is to work with. All right, we're going to do one more here that's going to be very similar, and we're going to do the hang lesson. So let's copy that one. Paste that in there. So you're not going to see much that happens after you issue that command, but your, oh, looks like I got the wrong one. Oh, no, it did work. Okay. So your application is going to stall at this point. The controls will stop working, and we're just going to hit the break all button, right, and see what happens. Well, since we know that we're hung, why don't we take a look at the threading window and see if we can figure out where that happened. So here you could click through and you can see all the different, different call stacks that you would expect, just like on Windows. And it turns out that there's a pretty obvious one down here, the Serious Sam engine, the lesson that caused the hang. So we're going to click on that one. And that's going to bring up our call stack and bring us right to the code. And you can see that clearly we're in a kind of silly little spin. Hopefully you won't have this situation, but it really is what you'd expect from the PC. And we can get out of that by simply dragging the cursor once again to unblock everyone, right? Move it down to the end out of being stuck on the counter and hit continue. And now your game console is going to be working again. So that's showing the threading window working as you'd expect with the call stacks, walking up and down the call stacks. We've used autos and locals or the equivalent. Yeah. Okay, and that is it for Nsight Tegra. Let me switch back to the slides. So Tegra System Profiler. Maybe you guys have already tried other profilers available to you today. Three of the most common are gprof, oprofile, and perf. Gprof is a little more unusual one. It's instrumentation based, so you're actually compiling extra code in, and it's going to go into the prologue and epilogue of every function, and it's going to do some extra work. So it's not a sampling profiler. It's trace based. In this case, and it's going to bloat your application, and it has other side effects, but you can get very detailed information. So it can be interesting. Many of these though require special operating systems, special builds. Maybe many of these could also be disabled by the vendor. We've seen perf not be available on certain devices. We've also seen some of these that could just simply be flaky with a crash randomly, so your mileage may vary. For our Tegra profiler, well, one of the great first things is that we actually have a GUI, right? It's not text-based like everything else. Some of those do have shells that you can work with, so you're not totally out of luck if you don't want to use our tool. But we do support Windows, Mac, and Linux. Mac support actually just came out yesterday, so that's great. It's sampling based. It's low overhead, so you'll lose a few frames a second, but not necessarily too many. And you can even adjust the rate in which you're sampling. We also get the full backtrace. And this happens even if you stop in like memcopy, for instance, right? So that's the big problem. If you don't have the specialized operating system, or compiled with the right compiler flags, then when it stops in the operating system, you often won't get that complete backtrace, which means that you're not going to get the data of where it is actually in your app, even though it stopped in memcopy. We can also do hardware counters. So that's going to be useful to be able to see the memory patterns, right? Are you putting your data close together so that you're going to get good use of the cache, or is it having to constantly wipe out those caches and reload certain areas? Okay, we're going to start our first session here in a second. Yeah, switch me. Great. Okay, we're going to come back to that same window that we were at before, D, work, main. We're going to go into our lessons and go into the soft math folder and then hit the install.bat. Okay. And just in case, because I swapped out devices, I'm going to rerun this one. So you guys won't have to do that last part. It was only, like I said, because I swapped devices. And now that we have the right application installed, we're going to come back to the desktop and, oops, where is my app? Okay. And this is the icon that you're looking for, the Tegra System Profiler. Let's launch that. It'll take a second to potentially install a few extra libraries down to your device so that it can properly extract all the information. So let's give that a second. Okay, great. And once the device is ready, then this window will populate. You shouldn't even actually have to click here. I've already set that up for you. But if you have, you'll just scroll down to the bottom and there'll be a SAM3. And actually, before we go further also, you want to make sure that you have double-clicked on this project, which would be a matching name up here, the soft math. And today, rather than starting profiling right from the beginning of the game, instead we're going to work in the middle of the game. So this is going to give you the best data, right? And instead of capturing me navigating the menus, we're just going to get right in the heart of it. So while that's happening, why don't you launch on your device the game again. And we're going to go through the same menu setup as before, except we're going to want to pick a slightly different level than before. So single player, campaign, custom levels, and the very bottom one this time, the NV particles. So this is going to cause a lot of extra math, right? As you can imagine, with sorting particles and the particle animation, right, happening, and difficulty doesn't matter. There are no enemies. And within a second, the game will load. It's all right. You don't need to switch back. Oh, you already did. Okay. Well, there's 6,000 particles here just swarming around in the middle. Obviously, it's not the. This is a developer-specific demo, not made to be flashy. And we'll go back to the Tegra Profiler. As I mentioned here, we're going to attach. So these can be off, but these are just startup options if you would like the profiler to start the app for you and how you'd like it to attach. And this is where your symbols are. So just like I mentioned in the debugger, right? We're going to want to take those addresses and resolve them to the functions, right? To give you the info that you're going to want. And we have both some operating system symbols here and the lesson itself specified. And over here on the analysis options, you'll have the second page where you can pick the frequency that you're going to sample. So right here we're doing just right in the middle at 1K, and some additional options for the call stack. Here are some compiler flags that we recommend. They're not absolutely necessary in most cases, but they can actually increase the quality of the results that are returned. And finally, I'm leaving these off just to make sure that the data is all limited and obvious talking points, so it's not too busy. But in the future, if you want to debug cache misses and your issues with memory, then you can turn these on and look at that information. And we're just going to click Start here. It was over in the corner. And we're going to let it go for about 15 seconds. And then we'll hit the stop key after 15 seconds has passed. It's going and doing some background work, resolving some symbols already. Okay, so I've clicked stop. Here's our results. So we're going to start in top-down view, and this is all the samples that we've collected. All right, so if we just expand all, we're going to see everything, which is pretty cool. We've gone and merged the trees together for every single sample, so you can see how it's branching, and you can see the distribution. Self percent is the amount of time that we're actually spending in that exact function. The app percent is an app-centric view of self. And this is going to be how long you're spending in that exact function, including time calling out into operating system supplied libraries like the graphics driver or libc. This also includes the kernel itself. So those different aspects. And then finally, the total percentage. The total percentage is going to be all other children within the app added onto it, so you have that compound information in your navigation. And here's a drop-down where we can then go to bottom-up view. And if we look in bottom-up view, you can see one of the interesting things here is that we have adds F3 and moles F3. This is a problem that a fair number of people have actually run into when they've switched, especially if they're going and using a system like Jam. So that's why we made sure that it appeared here. That this is a consequence of forgetting to specifically set your options for hardware floating point. So I'll switch back to slides, yeah. So here's the compiler lines that you would want to add. So MFPU, Neon with the backup of the VFP v4. These are the right ones for, or typically what a lot of people use for the Cortex A15. And then the floating point, you want to make sure that you're using soft FP or hard FP. Hard FP is a little harder to use, and it's only really supported well in the last 2 versions of the NDK, but there are other compiler changes you want to make. So for now, I would start here and just see what type of performance impact you get to your app and how it improves. We've had people reporting as much as 60% or more, so it can really make a major advantage to your game if you switch to properly use the hardware floating point. And this is easy to forget. Hard to notice, right? You wouldn't even see that typically unless you're actually going and looking in a profiler. How are we on time? Oh, okay. So I better switch to you soon. Okay. So rather than diving too much deeper, I think we are going to cut this lesson a little bit short. I will point out, though, right, that there's other functions to keep an eye out for, and oh, thank you. There's other functions to keep an eye out for. So in this case, the extra math work and some extra multi-threading work that we've put in here to slow the system down has outweighed the fact that I've also have left in the whole time, and you guys didn't notice, that we have a intentionally slow particle sorter in here. So I had swapped out the algorithm with something that was n squared, right, rather than a nice Q sort and doing some extra nice things like Q sorting very small structs and then using that all roughly in cache work to then do the larger structure copy of the real vertices to set up the particle buffers. And that's something good to look out for. And what we'd suggest is if you do then have a system like Archon, the remote console that we saw earlier, so you could build in variables into your system and go and switch between those, simply, and then rerun your trace again and find the impact of those different, of those different variables switching between the algorithms that you're using. And slides. Okay, and that's it for these first 2 tools. Oh, okay. Great. So don't forget to fill out your surveys, and I'll take any questions while I'm switching to the next presenter. Here's also the link to our forums if you have any additional questions, or our email address, which you can also email us at for additional support or questions.
Thanks, Daniel. If you would, in order to transition, go ahead and go onto your Shield device, and you'll see a little like a house icon to the lower right of the NVIDIA icon. Double click that and dismiss any one of the serious SAM processes, and that's just simply take your finger and drag it off to the edge of the screen, and that will just make sure that we're starting with no serious SAM processes running. Then as well, on your host machine, on your PC, go ahead and just close out any windows that remain, any instances of Visual Studio, Notepad, or any one of the other instances that are still running. Once that's all done, you should see an icon on your desktop for Set Up Tegra Graphics Debugger. Please go ahead and double-click that, and that's going to install all the APKs and information we need for the next lab. And that's about it. We should be ready to go. So my name is Jeff Keel. I'm the manager of the developer tools, specifically the graphics tools department here at NVIDIA. And what I'd like to do is share with you kind of a sneak peek, an early view of what we're calling the Tegra Graphics Debugger. This is our debugger for OpenGL ES and OpenGL applications that are running on our new K1 system or set of chips. I'm going to start off by giving you a quick overview of some of the graphics capabilities of K1. Then I'm going to do a kind of a tour of what's available in Tegra Graphics Debugger. Then we're going to have a few hands-on exercises for debugging some things. And again, we're using the same content for Serious Sam. I will echo Daniel's thanks for those guys for all the help that they've given us. And then finally, we'll wrap up at the end with any questions and Q&A. So Tegra K1 Graphics is, I know this is going to sound a little marketing, we're all engineers, and so it might leave a bad taste in your mouth, but I'm going to be honest with you, it really is a revolution in graphics for handheld devices. We finally have full DirectX 11 class hardware, and when I say that I mean, you know, tessellation, compute, obviously for OpenGL 4.3 bineless graphics, really everything you could have on a modern PC and on a modern console, you now have on a handheld device. So it really is a step function in terms of capabilities and in terms of performance on what you'll see on a handheld device. And so we really wanted to give you guys the tools to be able to take advantage of all the horsepower and all the features that we're going to be providing there. I do want to remind you that this is based on the Kepler architecture, and it has 192 CUDA cores, which just basically means it's pretty darn fast for its size and its power envelope. It can support up to 8 gigabytes of RAM. And it also can power a 4K HDMI device, output device, a monitor. So it's really beefy. You'd be amazingly surprised at how much horsepower you can get out of them on the graphics side. Tegra Graphics Debugger, what that does is it gives you the ability to do API debugging and API profiling, and API and GPU profiling from within any one of any type of desktop machines. So that could be a PC, that can be a Mac, that can be a Linux box. This is a completely cross-platform tool. We're going to be supporting all the different platforms that you would want to develop on. And there's really 3 main items that we have. We have our performance dashboard, where we really focus more on our real-time performance monitoring, and we give you some quick targeted experiments, the typical things you would expect, like 2x2 texture and things like that you can run to kind of narrow in on how your performance is doing. Then you can use a frame debugger, which performs a real-time capture of your applications. Your application is put to sleep. We do a real-time frame capture. We pause that application. We run that capture for a while, and then when you're done debugging and profiling, you just simply exit that capture. Your application comes right back exactly where it was until you can rapidly iterate. You can sit there and look at multiple bugs or multiple profiling issues all within the single run of your application. It gives you the ability to inspect all kinds of states and resources and everything, as well as you can do dynamic shader editing. So on the fly, you can be modifying your shaders, and then you can A/B between the original shader and the new shader to confirm if it fixes the bug or if it helps improve your performance. And then finally, we have our profiler. Again, rather than only focusing on kind of what-if type scenarios about, well, what if I tried to just dumb down my textures or whatever, we actually run different experiments all on the GPU pipeline and tell you exactly where your bottleneck is. We tell you, you are texture bound, you are shader bound, you are blending bound, whatever it might be, so that you can target all your optimizations rather than doing a bunch of experiments trying to figure out where that might be. All right, let's go ahead and get started. Okay, again on your desktop, you should have a small link. It's kind of a little bug with a sphere on it, and that's for the Tegra Graphics Debugger. Please go ahead and double-click that. And then yours may or may not be set up exactly as mine, but I'll go ahead and demonstrate it for you if it's already taken care of. You may have what's already a green indicator right here. If it is, don't worry, you can just sit back and watch what I do. But we actually support two different methods of interposing or intercepting the OpenGL API. If you have a non-rooted device, you don't want to root your device, all you have to do is just simply link one library that we will give you and then include 1.so in your APK file. And then you can run on any Tegra K1 device that is non-rooted, no problem. If you want to root your device, you don't have to worry about messing with your build, then you can do the procedure that I'm showing you here. And what we do is we just simply substitute our new driver basically in place of the one that's currently there. But obviously because we're messing with system files, it has to be a rooted device. So I'm going to go in here and I'm going to enable my interposer. It's going to go ahead and push all of my new driver files up there. And you can see also that it's gone ahead and enabled driver instrumentation for me. So again, if you just make sure that you've got that nice green check mark, you're going to be just fine. You may or may not have this show all button clicked. If you would just unclick that, it's going to make life easier. Now if you'll go over to your device, into your Shield device, go ahead and click the SAM button, SAM3 button on the device, on the screen, and it's going to load. And we're actually going to use the same level that Daniel was using originally. So I'm going to hit the A key, and then I hit A key for single player, again for campaign. I'm going to go up 1 so that I'm selecting custom level. I'm going to go up 2 so that I'm selecting the no enemies level, and then I hit just tourist level. And then once it's finished loading, you can select A in order to continue. Then back on your host system, we have the ability to do a quick refresh to scan for any processes that are now enabled for interposing for Tegra Graphics Debugger, and you'll see my SAM3 process is now there. If I double click that, I'm going to come right into my performance dashboard, and I'm already getting feedback in terms of how my application is doing. You can see here in my upper left-hand corner, this is just a simple software counter. We're just simply looking at your frames per second. We're in the 35, maybe 40 range, and a little bit bouncing up and down just a little bit. This one right here is going to give us an overview of what's happening in the pipeline. The topmost line, the lightish green one, is a GPU busy. It gives me an idea of how busy my GPU is. Then I've got a shader busy right below that. And you can see I've got a number of others, including my ROP or my blending unit, my color ROP, my CROP, and my ZROP. So you can kind of get a cross section. And these are kind of the default graphs that we give you. Then down here we've got a CPU graph. And this is giving you feedback on terms of how you're utilizing your CPU cores. You can see that Core 0 is fairly well pegged. Core 1's got a little bit of work, and then Core 2 and Core 3, not a whole lot going on there. And these are clickable so that you can enable and disable display of these. So if you happen to have maybe a couple of graph lines that are coincident and you want to be able to make sure that you see the other one that's behind it, no problem, you can just enable and disable those. Then what you can do is you can actually add a new graph to this because these are completely configurable. As a matter of fact, you can even grab one of these, you can pull it off and redock it. So everything is configurable, everything works kind of as you would expect in a normal docking view. Now if you would, come up to the View menu and select Signal Graph, and we're going to create a new one here. What I'm going to do is I'm going to start by clicking the button in the upper left-hand corner. This is my configuration button. I'm going to say Add, and you can note here that I've got a whole lot of different signals that I can look at here. But what I'm going to do is I'm going to come up here instead and click on the search menu and just type shaded. What that's going to do is that's going to search for that counter, that shaded pixel count. Double click that, and then you can change the color if you want. I'm not going to bother. Go ahead and select that, and then I'm going to dock it down here underneath my targeted tests. And you can see here what this is going to show me is all of the fragments that are currently being shaded every frame in the scene. And so it's just great feedback in terms of how much you're utilizing the GPU. All these are completely configurable. If you wanted, you can come in here and change the signals and everything. No problem. I'm going to go ahead and for the interest of time, I'm going to skip the target experiments. These are probably things that you've seen before. Again, you just run these to get a quick idea in terms of where your performance might be being spent. We're going to focus more on the profiler in just a little bit. So the first exercise, we've just done a quick summary, kind of gone through the performance dashboard, got a quick feel for how things are laid out there and what the different signal graphs are, and we went ahead and were able to create our own signal graph to get a feel for how that works. Any questions on that first section? No? All right, let's move on. Now we're going to focus a little bit more on our frame debugger. If you would, go ahead and press the button Capture Frame. this is where we're going to do that real-time capture. My application is actually still going to be running in the background. And we're going to go ahead and capture every single event, all the resources that are being used, and pull them into this host application. And what I'm going to do is give you a tour of some of the windows, the tool windows that we got available here. If yours isn't set up exactly as mine, that's no problem. All you have to do is just come up to the View menu and then select the one that I'm going to be speaking about. And you can see Scrubber View and Event View, so the first words are given here in the View menu. So in the Scrubber, what I can do, and also you want to have that current target view up as well. This is going to be helpful in this first section. In the Scrubber, what you can do is you can actually scrub through your frame and you can watch as things are being constructed. So you can see here I'm doing my shadow maps. And as I go a little bit further, I do a depth pass, and now I'm doing my diffuse pass. And you can see also that I highlight the current draw call in red. And by the way, if yours is flipped, you can just use this little flip button. They kind of, their render targets and their textures kind of flip their orientation, so we put this little flip button in to make it easier to look at. And then I come down here, and I'm doing some more of my diffuse. And you can scrub through every single draw call. This is really useful to kind of get a feel for how an engine works. This can be useful for programmers, kind of educating them on how things work, as well as using them for artists. Artists may not understand the intricacies of how a modern graphics engine works, and you can use this for them to kind of show them how a scene is constructed, what are the different passes, and help make them more efficient when they're constructing all of their content for your scene. Then as you notice, as I was scrubbing through here, you notice that this list down here, this events view, again, if you don't have it up, you just select View and Events. As I'm changing it, it's also scrubbing in here, and this is our event view that shows us each one of the API calls in this scene. So everything from all the draw calls highlighted in blue, all the way down to the very bottom when we do our final swap buffer. So you can see every single event that's in the scene. You can see all the different parameters, and we've got some different methods that you can display that with. But you can see all the different parameters and all the things that are involved, as well as if you happen to be doing multi-context, we can show you which context that's currently running on. And then also we show you the CPU and GPU time for every command. And so what you can do is you can sort by GPU time and quickly get a feel for where's my most expensive draw call, for instance, without even having run the profiler. You already know where you're spending your time in terms of which draw call is going to be expensive. And we're going to dive into that even deeper as we go. Also, if you happen to be using some of the new debugging extensions like KHR Debug, there's a thing called a KHR Debug group, and you can define what we call groups of draw calls or performance markers. Kind of if you're a D3D developer, you may remember those. And what that will do is that will enable you to do a hierarchy and basically make collections. So you can say things like, okay, the draw call from here to here, that's going to be my shadow pass. Then from here to here is going to be my depth pass, and then my diffuse pass, and my post-processing and everything. And that's really great because it's used throughout the UI. You would actually see them up here. You would see them down here in the events view. You would see them over in our profiler when we get to that. And so it's kind of used extensively throughout the UI, and that's really helpful. If you would go ahead and open up the geometry view. Mine doesn't happen to be open at the moment, so I'm going to select that. And I'm going to dock that over here. And this is going to show me my pre-transformed geometry for every single call. And as you can see, I've got kind of the top of one of those columns or colonnades or whatever they're called. Here's an actual column right here. And so it kind of gives me a feel for, are my vertex buffers and my index buffers set up properly? It's really important to make sure that your input data is set up, and this kind of gives you a quick overview to say, okay, that looks good. It looks like my parameters for my call are good, and so graphically it looks like I'm going to be able to render this column just fine. And then finally, on the right-hand side, I want to talk a little bit about the inspector view. We're going to talk extensively about this, but I want to give you a quick overview. What we've done here is we've taken all of the API state for all of OpenGL, and we've kind of split it as we go from the top to the bottom of kind of a virtual GPU pipeline. So you start up here at the vertex specification, and then you go through transform, your vertex shaders, all of your different tessellation shaders, rasterization settings, fragment shaders, pixel operation, and frame buffer. And then if you happen to be using a compute shader, the compute shader. And this is important because it really tries to take what is a very large amount of state, a very large number of different state elements, and split them up according to where they fall in the GPU pipeline. So it can really help you to understand, okay, if I make this setting, what is the actual change going to be, and where does it fall in the pipeline? Is it like a scissor setting? Where exactly does that happen? Does it happen after the geometry is rendered, or is it with fragments or whatever? So it kind of gives you an idea of where these things fall. So it's almost an educational tool in some ways. Last thing I want to show you is our resources view. That's going to be up here in the view menu under resources. I'm going to dock that here on the left. And what we do here is we go ahead and download every single one of the textures and render buffers and so on, and we give you a thumbnail of those so that you can see at a glance what's going on with all of your input and output resources. We also show you, again, all your buffers, so all of your index buffers and things like that. We show you a number of different ways to do some sorting and some searching. So these are kind of gross level buttons, so I can select just the type that I'm interested in. So I can just look at my drawables, for instance. So if I click on my drawables, and then if I left click on this, the back left, this is my swap buffer, it shows me all of my revisions for that buffer. And this is really great because you can kind of trace through things and look for where modifications to that buffer is happening. So I can go, okay, yeah, that's the one. That's the draw call that it did. That's revision 12 on event 3893. And so I can really zoom in on that event and know, okay, that's where I want to start my debugging, or that's where I want to start my performance tuning. And then you can, if you go ahead and click on the graphical view, and what this does is this gives you an image of that you can manipulate and you can mouse over. Unfortunately, we've got a bug where we're not showing our RGB values. Again, this is pre-alpha software. Please bear with us. And I can sit here and mouse over. I can see a quick swatch of what that color is. Then I can grab it with my left mouse button and drag and move it around. And then I can use the mouse wheel to actually zoom in and start to look at some of those finer details. You know, the screen on the Shield device is a nice screen, really gorgeous and everything, but it's a little bit small to see some things sometimes, so this helps us to see what's going on in the finer areas. And then also I can save that image off to a file if I want. And then finally I've got a memory view as the last tab. And you know, typical stuff that you would expect in any memory view. You can do casting. If you happen to be looking at a vertex buffer, I can cast it to either 16 or 32-bit floats. Again, normal stuff that you've seen in memory views and in other applications and IDEs. All right, so with exercise 2, we did a quick tour of some of the capabilities that you've got, some of the UI elements that we've got in the host when you're into frame debugging. Again, we looked at the scrubber and event list and everything like that, but are there any questions on any of the items I've covered there? No? Looks good? All right. Let's go ahead and dive in on an exercise and try and fix a bug with our HUD. Now, actually, I'm going to go over here first. Now, you'll notice I'm going to scrub all the way over to the end. And you'll notice that the final rendering image doesn't happen to have any of the HUD items that were on Daniel's one. And so, you know, we typically have like a health item and a bullets and all that kind of stuff, but that's not showing up. So it looks like we have a bug here. Now I'm going to switch back over to Tegra Graphics Debugger. And in the scrubber, I'm going to use the shift and left mouse button click and drag. And I'm just going to highlight this end section right here. And I'm going to click on that. I'm just going to select one of the draw calls here. Now, as you can imagine, the typical way to do a HUD is you finish all of your rendering, you get your final scene, and then at the very end you go ahead and apply those decals to the bottom. And that's exactly what they do here, but it looks like I've got a rendering issue where they're not showing up. Okay, so let's go ahead and dive in to see if we can figure out what the problem might be. Well, one issue that can typically be is that you don't have your vertex attributes set up properly, and therefore your geometry is not going to be rendered. Even though the pre-transform geometry looks good, your post-transform won't work properly. So I look here, and it looks like, okay, all of my vertex attributes are enabled. Okay, that looks fine. All my vertex buffers are bound. So everything looks good there. I don't think that's where my issue is. Now what I'm going to do is go down to the fragment shader. So I'm going to select the pipeline navigation, and I'm going to go down all the way down to program and make sure that my program, basically my fragment and my vertex shader are set up appropriately. And it looks like right here, yeah, everything looks fine. Everything is link status is okay. Everything is compiled, so that looks good. It looks like my program is set up okay. Let's go ahead and click on the resource. Maybe I've got a wrong texture bound or there's something wrong with the texture. So click the link here. That's going to open up in my resources view. And you're saying, okay, that doesn't look very good, that's white. But it turns out they do the typical method of using alpha in order to define where the characters are. So I'm going to click my alpha button right here. And you can see here that indeed my alphabet soup looks pretty good. All my letters are there. So yeah, that looks fine. It looks like texture is not my issue. And you know, it looks good. I don't have any problems there. So now let's go ahead and click on our fragment shader. So right back here on my program page, I'm going to click on source for the fragment shader. I'm going to expand that out, make it a little bit easier to see. And then I'm going to scroll all the way down to the bottom because that's where they're doing all the work for the fragment shader. Now you may wonder, why is the file that large? The reason why is that the guys at Croteam use kind of an Uber shader and lots of macros in order to compile their shaders, and they can compile them across platform. So this same shader is used for HLSL, it's used for GLSL, and so they really use lots and lots of different macros and things to be able to enable that. And so if we scroll all the way down, this is where we find the true entry point, and we can start to inspect what's going on here. And so it looks like we do a simple texture 2D, and then we unpack some color to renormalize things. And then it just simply, multiplies the impact value. Everything here looks fine. I don't really see anything necessarily problematic here. So let's go ahead and close that shader, and let's look up towards the top of the pipeline. Let's look at the vertex shader, see if we can find the problem there. So go ahead and go back, close that window, go back to your program in your API inspector, and click Source. I'm going to expand that out again. And again, I'm going to go ahead and scroll down towards the bottom. And specifically, I'm going to look around line 642. Okay, so this is my simple vertex shader. And I'm walking, okay, I go ahead and multiply the input position by the matrix, and then, there's my NVIDIA bug. Went ahead, and while I had a texture coordinate coming in, I didn't transfer it to the outgoing, and so the texture coordinates never made it down into the fragment shader. Therefore, I wasn't able to do anything. Okay, this is something that we can easily fix using shader editing. So what I'd like you to do is go ahead and right-click and select Edit. And then you may need to just kind of move things around a little bit. This is going to be our compile results showing up here. And on the right-hand pane, the left-hand pane is your original shader, and the right-hand pane is the one you're going to be able to edit. I'm going to, in the right-hand pane, again, scroll down the line 642, and then I'm simply just going to comment or uncomment that out. So I'm going to select from VS out all the way to the beginning of the comment, delete that, and this is a macro that they use to basically sample from or grab a value from the input input structure versus the output structure. And then I'm going to right-click, I'm going to say compile, and you can see here my window for my current target view changed. But I'm going to go ahead and go over to the shield, and you can see already that there's my HUD. So I got my life over there, my bullets over there, everything looks to be functioning properly. So, all right, so for exercise 3, we were able to find a rendering bug. We had a missing HUD. We used the scrubber to figure out exactly where those calls might have wound up. Then we used the API inspector. We looked at a number of different aspects of the API, and it looks like those were all set up properly. Then we used the resources view to make sure that our texture looked okay. And then we inspected some of our textures using the shader editor view, figured out which one was at fault. It was our vertex shader. Was able to make a quick edit, fix the shader, and then we can go ahead and check things out. And also, by the way, you can use A/B to confirm things. If I go back to my shield, and then you notice up here at the top of my shader editor view, I can click the A button, and then my HUD goes away, and I can click the B button, and then it comes back. So you can A/B between the two shaders to make sure that things are exactly as you expected. Any questions there on our third exercise? No? Looks good? All right, we're heading into our final exercise. We're going to try and figure out what's going on with our performance. All right, go back to my tower. Go ahead and close the shader editor view. And then if you would, just right-click on the scrubber and select Profile Frame. Now what this is going to do is this is going to run all those experiments I was talking about earlier to figure out exactly where in the pipeline my GPU bottleneck might be. While it's doing that, I'm going to go ahead and dock that window, make it a little bit easier to use. And you can see here, it's brought up my profiler window and it's giving me a whole lot of results, and I'm going to break things down for you a little bit. Move things around just a little. In my upper left-hand corner is my collection of draw call groups. What we've done is we've gone ahead and given you the first group, which is based on all the events in that frame. But what you can do is you can go ahead and make different groups depending on such things as those KHR debug groups that I was talking about earlier, or you can also do it based on shared state. We actually call those state buckets. Now, if you would, click on this button that's right here. It's kind of a little notepad with a pencil on it. Go ahead and click on that button. That's going to bring up my window to edit those state bucket groups. In this case, I'm going to choose to make state bucket groups based on ones that share the same fragment shader and same vertex shader. And then go ahead and click OK. Once that's done, I'm going to come up here and resort my buckets based on GPU time. And that's important because, for instance, let's look at this one. This one is a bucket that has a single draw call, and it takes, about 12 milliseconds, almost 13 milliseconds to run. And so I could go in there and I could try and optimize that individual draw call and probably make a pretty decent impact on the performance. But look up here, just 2 buckets up here. There's 18 different calls in this one, and this takes almost 20 milliseconds to run that entire bucket. The reason why you want to use state buckets is it allows you to take your optimization, and rather focusing on one draw call, you can focus on an optimization that may impact a whole lot of draw calls that therefore will improve your performance even more because it's actually hurting your performance more. Okay, so it really enables you to take that optimization effort and amortize it across a bunch of draw calls and therefore get a bigger bang for your optimization buck. Now, of course, after saying all that, I'm not going to follow my own advice. I'm going to go ahead and go after this draw call. And this is my FXAA pass. All right, so click on that draw call in that state bucket. We see that your event numbers may not be exactly the same, by the way, but it's event 3788. And I'm going to come down into my fragment shader, and I'm going to open up the source code for that. Expand that out a little bit so it's easier to see. And this is, again, our FXAA pass. So if you would, scroll down to line 1436. This is where the shader starts, right there. This is our FXAA shader. And you can see here, obviously we passed up by a whole bunch of subroutines as well, but you can see here it's doing a whole bunch of different texture reads, and then it's going to do a whole bunch of math and mins and maxes and everything to figure out exactly what we want to do for our FXAA. And we can see already that all these different passes, it's a pretty expensive shader. Now, this is not really a class necessarily on shader optimization, so we're going to make things a little bit simpler. And that's going to be the thing that we're going to use to try and see what the impact on the profiler is. So if you would, right-click and edit shader, just like we did earlier. And let's go ahead and scroll back down to line 1436. Actually, we're going to go to line 1440. So right after we grab the texture coordinate out of the input variables from the pixel shader, I'm going to just do a # if 0. I'm going to basically comment out a gigantic block of code. And then what I'd like you to do is scroll down to a line around line 1765. That's towards the end. And this is where we actually do one final read of the texture and then put my end if there. So what I'm going to do is I'm going to go ahead and do my texture coordinate, grab that, go ahead and do a single sample rather than all the different samples and all the different averaging and all that kind of stuff I'm going to do. And that's going to be what my new FXAA pass is. So go ahead and right-click and say compile. You can see that my target is updated. I'll go ahead and show you that on the shield. And you can see there's really not that much of a difference. Although the sky looks like it's got some issues going on there. Not quite sure what's going on. I'm going to go back to my tower, back to my device. And now what I'm going to do is I'm going to go ahead and dock this window. And now I'm going to come over to my profiler view, and I'm going to lock this profiler view. The reason why is I want to make sure I hold on to this data as I do my new profile. And then I come over here to my refresh button and rerun that profiler. And again, just like last time, it doesn't work. So just come up to the view menu and just say profiler. That's going to open a new instance of the profiler. I'm going to dock that on the right side. And it's going to reprofile that scene, but it's going to reprofile it with my new shader now. So rather than having the really expensive FXAA shader, I've got a much cheaper FXAA shader running. My results are out on the host. And I'm going to do the exact same thing I did before. I'm going to go ahead and create state buckets. Now note, my draw call is going to be the same here. So first what I'm going to do is I'm going to find my event. So this is event 3788. I'm going to scrub down, and I'm just going to make a note that this is taking, let's see, about 2.8 milliseconds, right? Yeah, about 2.8 milliseconds, 28674, all right? So now what I'm going to do is I'm going to go ahead and create my same state bucket. So I grab that button up here with the little pencil, fragment shader and vertex shader, hit OK. And now what I'm going to do is going to try and find that state bucket so that I can compare those same two passes. Actually, I'm going to sort by GPU time. There we go. So this is my same shader. We can see 3788, 3788. And we can see here that I'm still shader bound, but the reason why is that it's not because of ALU anymore, it's just because that's the only thing I'm doing. But the key that you see here is I'm no longer doing all this texture work, and so I'm no longer texture bound. All right, and what you could also do is you can actually click in here. You can see I've got a little memory highlight here, and I can click in here and get a feel for the number of texture reads I had. I had 2 million texture reads with the original kernel that I was running, original shader. Now, sorry, 22 million. Now I only have 3 million. So you can see there I've completely eliminated my texture bottleneck. I'm still a little bit shader bound. That's simply because there's not a lot of ALU going in there. There's not a lot of other bottlenecks in there. And then we also show you a number of other different graphs. I'm not going to go into the details, but we show you, kind of a breakdown of all those different values that we have here because of the summary window. We should break those down. And then finally, we also show it to you in a table at the bottom. So if you want to look at it in a more tabular format, you can go ahead and look at those in the raw data. All right. So again, we had a bottleneck, or we had some GPU issues that we wanted to look at, so we used our bottleneck determination to figure out exactly where our bottleneck was. We were able to do some dynamic shader editing, so we could look at the before and after of the bottleneck determination and actually see, look, a lot of my texture bandwidth has been saved now because I was able to improve that shader. And again, we could do lots of different data mining into that in order to be able to understand the frame and understand exactly where the bottlenecks are for each one of those state buckets. And that's about it. Any questions on that exercise or any one of the things that we've talked about today?